Hi guys, welcome back. So today we're going to be looking at accuracy and precision. So we need to distinguish between the two, and we need to communicate that uncertainty within a particular range to an appropriate precision. So success criteria, we're going to calculate uncertainty of different measurements. I've got a few different vocabulary words there for you. Some of these terms you may already be familiar with, but just be careful with accuracy and precision because there is a very particular scientific definition that I want to go through with you. Okay, so let's start off with the accuracy and precision. So the difference between something that's accurate and something that is precise is that when something is accurate, that means that it's close to the goal, close to where we want it to be. When something is precise, it means it's hitting the same spot over and over and over again. So something can be precise without being accurate, and something can be accurate without being precise. Okay, so I've got these images here to sort of help us to demonstrate what I'm talking about. So if we look at this particular target here, this is the goal. We're trying to get the bullseye. And if we look at this one here, we can also sort of see these guys are both pretty close to that bullseye. So they're both pretty accurate. The difference between the two is that this is very precise because if you have a look, they're all very closely nested in together, whereas here they're a little bit more spread out. So they're not as precise. If we have a look at these diagrams here, on the other hand, these do not have very high accuracy because again, the whole goal, we want to try and get it into the bullseye. So they're not anywhere close to the bullseye. But we can see here that we've got a pretty precise value. And this is one of the big issues with science is that sometimes we think just because we've got a very precise value, that means that our claim is valid. But sometimes there's some error with the experimental procedure. So say, for example, if you have a ruler that you're doing measurements with and you're not paying attention and the end of the ruler is snapped off, and so rather than measuring from 0, you're actually measuring from 0.2. So your whole measurements are actually going to be off by 0.2, even if it's simple enough to go ahead and measure everything and you get a very precise response, it's not going to be accurate. And similarly, with this, it's not precise and it's not very accurate because it's not near that bullseye at all. So with science, the goal really is to be accurate and precise. So to do that, we have to reduce experimental error. So the way that we sort of reduce experimental error, I'm just going to go back up to the top here actually, because this is a pretty simple one here. So we're going to calibrate a machine. So if you've ever had some sort of scale, okay, there's usually like a couple of different buttons down the bottom. One of them might be like the mode. One of them might be a button called tare. So that's spelled T-A-R-E, tare. And then you might have like some other button, whatever. Go have a look at some food scales. They have them on sale at Kmart. You can see what the different buttons do on a scale. And then you've got your reading that comes out up the top here. And so what we can do as a scientist, say we wanted to measure a particular amount of a chemical. So we put a beaker on our scale. Let's get a different color to draw our beaker. So we get our beaker and we're going to pop that on our scale. And then this is going to come up with a reading and that come up with something like maybe 20 grams. And so what we would do is we would hit the tare button and then that would reset that back to 0. And the reason that we want to set this to 0 grams is because we're going to add a chemical into our beaker. We want to weigh out an exact amount of that chemical. And so now that we've put that chemical on there, that's going to add our value. And so let's say we wanted to put 10 grams of something in there. So now we've got 10 grams of that particular substance. So it's a really neat little button if you haven't seen it before. Again, you can go, Kmart is still open. You can go play with the food scales at Kmart to see what I'm talking about. Or your scales at home, you may actually have a tare button on your scales at home. And the reason that you might use that button at home on your scales that you use to weigh yourself is because sometimes when you have an uneven floor, it actually makes the weight a little bit off. So if you tare it at that particular point, it will recalibrate it to that point. So calibration is really important to make sure that we are getting accurate and precise measurements. The last couple of terms I want to talk about, I don't want to spend too much time on this though, qualitative versus quantitative. So we've spoken about types of data numerous times before. So when we are dealing with things that are qualitative, we are dealing with some sort of category, so some sort of descriptive term. And this could be broken down into nominal or ordinal. So when I'm talking about nominal, nom is Latin word for name, not just for eating food. So nominal is referring to things like the types of cars, or like the brand of handbag, or like your favorite type of fruit, for example. So you're naming the actual object. The other type of qualitative data that we have is ordinal, and that's something that you put in an order. So for example, bronze, silver, gold, or maybe like for example, your grades A, B, C, or D. Quantitative data, so that's data that has some sort of numbers involved, and that comes from this word quantity within quantitative, and we have two types of quantitative data. We have the measured, and then we have the counted. So when we measure it, that's going to be our continuous data. So continuous data is measured. And then we have discrete data, which is counted. So for example, if I was to weigh myself, depending on the type of scale that I'm using, if it's an accurate scale, I might be able to weigh myself to like the third decimal point, for example. So I might be 75.628 kilograms. If I had jumped on a scale that was a lot less accurate, so if you've ever seen those scales, they don't have the digital reading on them. They've actually got like a little, what's it called? Like a little handle thing, and the handle thing like moves around and spins and everything. If you've got one of those like old school scales, you'll know what I'm talking about. But they are not super accurate. So I might jump on that and it'll just look like it's going to be about 76 kilos if I looked at that scale. So that's why it's continuous, because I can continue to measure and I can continue to get more and more accurate. And also because we can continue to add decimals depending on the accuracy of our scales. And then discrete data is just data that's counted. So for example, the number of cars in the car park. So pretty straightforward stuff. Okay, so let's have a go at some of these questions now. So I want you to go through and I want you to actually define these three terms as part of your vocabulary list. So I'm not going to do that question for you, but let's have a go at question 2. So describe the accuracy and precision shown in figure 4. So you can tell me that it's highly accurate, highly precise, or you could tell me that it's not very accurate or not very precise. So again, remember the goal with this is to hit the bullseye. So I'm going to say that it has low accuracy, okay, because it hasn't hit that bullseye. But I would say that it is highly precise, because precision just means that I'm hitting the same spot over and over again, and it looks like they've hit the same spot over and over again. Okay, so a student measures the mass of a substance and finds it to be 12.31 grams. They state that their measurement is both accurate and precise. Identify errors in this student's statement. If you take one measurement, so like if I've got my target, right, and I make one measurement, how do I know where on that target that measurement is going to be? I have no idea. So that's why in science we always take an average of things. And because he's just done the one, we're not able to take an average. So we're not actually able to determine whether it's precise or whether it's accurate. Because we could have one dodgy scale that's really, really off, or we could have a perfect scale that gives us the exact value that it is, but we have no idea because we don't have any other values to compare it to. So minimum you would need to do 3 trials, and that's why we always do 3 trials here at school. Okay, contrast qualitative and quantitative data. Provide an example of each to illustrate your point. Again, this is one that I want you to define, so I'm not going to answer that question for you. But let's have a look at question 5 here. A standard weight was measured on an electronic balance and the following measurements were made. So if you don't know what a standard weight is, basically there's some big mass that they have in some locked vault somewhere, and they say this is the mass of exactly 1 kilogram here on Earth. And so what they've done is that they've made up smaller weights, 10 grams, 20 grams, 30 grams, and they say these are the standard weights, and we're going to compare every other weight to that. So what we're actually testing here, it's not the accuracy of the weight, we're actually testing the accuracy and the precision of the scale. Okay. All right. So if we have a look, let's keep reading this question now. So a standard weight, blah, 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 blah. So 9.9, 10.2, 8.9, and 10.9 grams. Classify these results as accurate and or precise. Provide reasoning to support your answer. Okay, so in this case, our target, our goal is 10 grams, right? So that's our bullseye in this particular case. We've got 9.9 grams, which is pretty close. Hold on, I might move that in. I'm going to do 9.9 grams is pretty close. We've got 10.2 grams, which is pretty close. We've got 8.9 grams. That's getting a little bit dodgy. And we've got 10.9 grams, which is also a little bit dodgy. So that's like about a 10% error there. So classify these results as accurate and or precise. Straight up, I don't think that this is very precise. Scales nowadays have a lot more of these precision factors built in. So I know that when I hop on my scales at home, if I jump on and I weighed 75.2 kilograms, I jumped off the scale, I moved the scale to a different spot in my house, and then I jumped on it again, then it will say, okay, so you might have had a difference of about 200 grams, but because of the features of the scale, it actually just will say, oh, you're still 75.2. And that's because it says if there's a difference of less than a certain amount, then it's not actually any different. And so it'll give you the same result over and over and over again. So it's pretty precise, but how accurate is that actual measurement? Okay. So, I would say this is not particularly precise. Let's check for accuracy. So to do that, to check that it's accurate, I need to find the mean of all of these. So the mean is going to be equal to the sum of all the scores divided by the number of scores. So we're going to have 8.9 plus 9.9 plus 10.2 plus 10.9 divided by 4, and that's going to give us our average. So 9.975 grams, I should write the units there as well, is going to be our average score. That is pretty close to 10 grams. So I would say that this is actually a pretty accurate set of scales. It's just not a particularly precise set of scales. All right, let's do one more example of this. 3 students measured the concentration of sodium chloride solution. They each made 3 measurements of the mass of sodium chloride in grams remaining after evaporation of 100 grams of solution. The results are shown in table 1. The true value of sodium chloride is 35.9 grams. Interpret the results to determine which student was both precise and accurate. Okay, so let's just do this really quickly. Let's find the means of each of these. I've got the working just for student 1 on how to find the average, and I've just gone ahead and followed that same process to find the average for the other 2 students. So let's have a bit of a closer look at each of these. So student 1, you can see here 34.7, 35.4, 36. There's a little bit of variance, so I wouldn't say that this is the most precise, but it's not too bad. And this has an average of 35.4 grams. When I compare that to 35.9, it's not too far off. Let's have a look at this next one. 41.2 grams, 31.9 grams, and 34.1. Ooh, so we can see here, this is a lot less precise. It is all over the shop. But if we have a look at the average is 35.7. So this is actually closer to our target value. So this student is highly accurate, but he's not very precise. I might just delete that. Okay. And then this last one, so 38.9, 39.1, and 39.2. There's only a difference of about 0.3 between these 3 values. So this guy here would be highly precise. He's very good at doing his measurements. The only problem is that his average works out to be about 39.1, which is quite different from our original value here. So he's very precise, but he's not very accurate. And that could be down to something like maybe he's including the weight of the beaker or the weight of the paper that the sodium chloride is on when he should have tared the scale so that he wouldn't have included that paper, because that could be what's happening here, because he's very precise, he's just not very accurate. Okay, so let's summarize. So this guy is, moderately precise, moderately accurate. This guy, highly accurate, but not precise, because he's got so much variation within his scores. And then this guy here, very precise, not very accurate. All right, so I'm going to leave you guys to have a go at question 7. So investigate, evaluate, and communicate this last sentence. And I will talk to you guys in the next video. Have a great day.